Hello, everybody, and welcome to the Latin American webinar on physics. This is the webinar 178, if I am right. I guess I'm right. Yes, I'm right. It's 178. We have a very special guest today, sorry. He is Kevin Kelly. He is an assistant professor at Texas A&M University. Before becoming a professor, he was postdoc. He got the PhD. He got his PhD from the Northwestern University, and after that, he had done a postdoc at Fermiland and CERN. The webinar title of the talk that we're gonna give Kevin is what's lurking around the corner at the neutrino experiment. And Kevin, welcome to lawphysics, and you can start whenever you are ready.
Great. Thank you, Roberto. And thank you all for being here. It's a very big pleasure. So I'm excited to share about some of my recent work, about why I am very excited for the future of the community of neutrino experiments, and why I am optimistic that there are discoveries ahead. So I'll share some perspectives about that. And yeah, let's get right into it. So these neutrino experiments are naturally designed to do neutrino physics, and so I would be remiss if I spent a whole hour talking about great discoveries ahead without talking about some of the bread and butter things that these facilities can do. Things related to, for instance, neutrino oscillations at long baselines. But then I'm going to devote most of the talk to thinking about new physics associated with neutrinos. So instead of new physics, I'll talk about new physics. So situations where neutrinos are participating in physics beyond the standard model. So BSM physics with neutrinos. And then with the last bit of time in the talk, I'll talk about things that have nothing to do with neutrino physics. So beyond the standard model physics that we can look for in these neutrino facilities, using the same detectors and equipment that's designed to study neutrino physics and neutrino oscillations, but completely orthogonal to the main mission of these facilities. So let's talk about neutrino physics. Why are we interested in these facilities in the first place? Well, the main driving reason that we study neutrino physics and why we find it so intriguing is that the recent discoveries over the last 20 or so years have pointed in this direction that neutrinos have mass and that leptons mix. And this is key evidence for physics beyond the standard model, because within the standard model, the neutrinos should be massless states. However, from many experiments, especially solar neutrino experiments and atmospheric neutrino experiments, we know that there are non-zero mass squared splittings between the three different mass eigenstates of neutrinos. One of those mass squared splittings that has the moniker of the solar mass squared splitting is on the order of a few times 10 to the minus 5 electron volts squared. And the larger mass squared splitting, which we originally detected from atmospheric neutrino oscillations, is about a factor of 30 larger. One interesting thing about this is that we don't know, because of how oscillations proceed, whether neutrinos follow the so-called normal mass ordering, where the state that we call M1 is the lightest of the three, or the inverted mass ordering, where actually the third mass eigenstate is the lightest of the three. So this fact that neutrinos have masses in the first place was completely unexpected within the context of the standard model. Couple this with other experiments, for instance, searches in the laboratory for deviations at the endpoint of tritium beta decay, or searches for phenomena that violate lepton number, like neutrinoless double beta decay, as well as searching for the imprint of massive neutrinos on cosmic scales through their impact on clustering and large-scale structure formation in cosmology. All of these other ways of looking for neutrino experiments have come up empty-handed. Now, that is an unfair way of saying how these experiments and these tests have performed. They have performed extremely well, and they have set extremely stringent upper limits on how big the neutrino masses can be. So we have this kind of twofold situation where, coming from below, oscillation experiments say that neutrinos have to have some mass, but all of this other evidence, especially cosmology, says that mass can't be too big. And so we know that neutrinos have masses, but they have to be extremely small. much smaller than any of the other charged fermions in the standard model. We don't know why neutrinos would have such peculiarly small masses. So in the context of oscillation physics, how do we actually measure these oscillations? Well, if you work out the phenomenon of neutrino oscillations, what you'll find is that an oscillation probability for a neutrino to start as one flavor eigenstate and be detected later as a different flavor eigenstate has terms like this sine squared term show up everywhere. And the argument of that sine squared term has this mass squared splitting, delta m squared, as well as a baseline length, the travel distance of the neutrinos, L, and their energy, E nu. And if you can get this delta m squared L over 4E argument to be close to something like pi over 2, then these sine squared terms will be relatively large, and you can have hope for detecting oscillations. Now, there are two distinct mass squared splittings that I showed on the previous slide, so you can have this happen for different combinations of L and E. And what's shown on this figure here are regions of space in terms of the travel distance of neutrinos versus their energy, where oscillations are maximized from that delta m squared 3.1 atmospheric mass squared splitting, or that delta m squared 2.1 solar mass squared splitting. And these are just a handful of neutrino experiments, but these are certain ones that are operating now or will be operating in the near future that occupy this L and E parameter space. So what do we do with this? Well, we measure neutrinos at these different places. I'll go into more detail about this later. And by measuring this, we can understand more about these oscillation probabilities. This is the probability of starting off as a certain flavor and staying that flavor versus converting into a different flavor. And by measuring how much the oscillations have happened at these far distances, we can learn something about the mixing of neutrinos from this phenomenon. So to go into that in a little more detail, let me think purely, and I'll think about this much for the rest of the talk, about the idea of neutrinos that are created in a proton accelerator complex. So I call these accelerator neutrinos. The simple schematic is what's shown here. We have a proton beam that's been accelerated to relatively high energies. Think 10 GeV or 100 GeV maybe. And that proton beam hits a target, something like graphite. When that happens, you have a bunch of standard model interactions, and out of that come things like charged and neutral standard model mesons, pions, kaons, etas, etc. These mesons are situated, or sorry, the target is situated in a magnetic focusing horn, whereby you can select the sign of charged mesons that you wish to go in the forward direction. So in standard cases, you operate this so that positively charged mesons go in the forward direction and negatively charged mesons go away from the forward direction. You can also switch the polarity of this so that the opposite is true. And if this happens, then your positively charged mesons will be going forward. And if you have a pi plus, for instance, it will decay into a muon type neutrino most often. You could also have a situation where a charged kaon is going forward and decays to something like an electron neutrino in a three-body decay like this. But this process is relatively rare. So we expect to have a large abundance of muon neutrinos with maybe some small contamination of electron type neutrinos, as well as a small contamination of antineutrinos because the magnetic focusing isn't perfect. You build a neutrino detector downstream of this, several hundreds meters away, and you look for interactions. So if a muon neutrino comes in and it interacts in a charge current way, it'll kick out a charged muon. That'll leave something like a long muon type track in the detector. Or if you have an electron neutrino and it converts into an electron, you'll see a different event topology in the detector, maybe something like an electromagnetic shower from that E minus passing through the matter. So you take this and you measure the zero distance, quote unquote, rates at this near detector, this muon neutrino rate, this electron neutrino rate, which we're going to assume is much, much smaller than the muon neutrino rate. And then you build a second detector very far away. And this is not to scale. And what do? Well, you effectively repeat this same experiment. So you look for muon type interactions in the far detector, and from the far detector muon neutrino rate relative to the near detector muon neutrino rate, we can learn something about this survival probability for muon flavored neutrinos. And similarly, by measuring electron neutrino rates in the far detector, we can ask something about the electron neutrino appearance probability of nu mu to nu e appearance in this far detector. And so by comparing these near and far detector rates, we can learn something about oscillation probabilities. So just a quick advertisement about what we can do now in terms of neutrino oscillations versus what we can hope to learn from upcoming experiments. This is a way of presenting our knowledge about how much mixing there is in the leptonic mixing matrix in the context of one of these unitarity triangles. These are often analyzed in the context of the quark sector, where things are much more precise and powerful, where we've got a lot of work to do in the neutrino sector in constructing these. So our current data say that we can live anywhere inside this green wedge. And this is of particular importance for mixing in the neutrino sector because the larger the area this triangle is, or the further the best fit point is from the x-axis in this figure, eta equals 0, the more CP violation there is in the lepton sector. This is connected to questions about why we live in a universe that's dominated by matter instead of antimatter, for instance. So currently we live somewhere in this green wedge, which is relatively imprecise. But with future data from experiments like DUNE, Juno, T2 Hyper-K, and IceCube, we expect that future measurements will be something as precise as this much smaller red banana. So in the next 15 years, we will drastically improve our precision for understanding neutrino oscillations. So shifting gears now to go away from the standard oscillation physics about neutrinos, I want to talk about new physics that might be present in these scenarios. So when I showed this picture comparing our near detector measurement to our far detector measurement, I said that I made this assumption that my near detector electron neutrino rate is much smaller than the muon neutrino rate. And I want to ask the question, what if that's not the case? What if there is a deviation from that expectation? And could such a deviation be evidence of beyond the standard model physics? So this is a situation that has happened before. For instance, at the LSND experiment, the liquid scintillator neutrino detector at Los Alamos National Lab in New Mexico in the US. This was a facility that operated very similar to the sketch that I showed above. Instead of making neutrinos from mesons decaying in flight, it mostly made mesons from decay at rest in this copper beam stop, but mostly from pi plus decay. And if you make neutrinos from a stopped pi plus, you should expect to see muon type neutrinos, as well as subsequent electron type neutrinos and muon type antineutrinos from the mu plus decay that happens as well. Notably, there are no electron antineutrinos in this set of three, except for if you have some sort of oscillation from nu mu bar into nu e bar. And so Los Alamos looked for evidence of electron antineutrinos in this liquid scintillator detector, and they saw a significant excess above their expected background. Everything that they saw in terms of their data is these black data points, and their expected backgrounds are these red and green histograms. This blue curve, this blue histogram, is the expected contribution that they're claiming comes from nu mu bar to nu e bar oscillations. And so this corresponds to an oscillation probability at these very short distances. These are only tens of meters at the level of a few times 10 to the minus 3. I'll get to why this is problematic in a minute. But I will say that an experiment was designed to test this anomaly, and that was the Mini Boone experiment at Fermilab in Illinois in the US. The Mini Boone experiment aimed to test this LSND anomaly at very different baseline length and neutrino energies, but a very similar L divided by E. So slightly higher energies, slightly longer baselines, where some of the systematic uncertainties are very different for this type of physics. And Mini Boone operated much in that accelerator neutrino fashion that I motivated earlier. Now, Mini Boone looked for electron-type neutrinos in a muon neutrino beam, as well as flipping the current of the horns, they made a muon antineutrino beam and looked for electron antineutrinos as well. And the most recent results from mini-boom claim to see a significant excess of these electron-type neutrinos or antineutrinos just under the 5 sigma level. Okay, so what happened? We seem to have this picture of accelerator neutrinos, or comparable at LSND, where something broke down in this picture of making a pure muon neutrino beam and seeing very few electron neutrino events in this detector. So the simple question you could ask is, was there new neutrino physics modifying the propagation of neutrinos in this hundreds of meters or even less in the context of LSND? Now, if you calculate oscillation probabilities using the same formalism I mentioned above, the delta m squareds that we know from solar physics, from atmospheric physics, all of that, are much, much, much too small to get any significant oscillation probability in experiments like LSND or mini-boom. So in order for it to come from this kind of oscillation type physics, you need a new mass squared splitting, a new mass scale, delta m squared, that's much bigger than the order 10 to the minus 3 electron volts squared we've been working with when talking about long baseline oscillations. So if we add in this new mass scale, we also have to worry about things like the invisible decay width of the Z boson that says that there's only 3 neutrinos that interact with the standard model weak interaction. So if we add this fourth neutrino, it has to be what we call a sterile neutrino, a new gauge singlet that doesn't interact with the standard model weak interaction. That doesn't stop it from mixing with the standard model neutrinos because they share the same quantum numbers. And so we can think of this fourth neutrino as having a new mass squared splitting and some mixing with the standard model. And if we do that, we can ask, okay, what does LSND see? What does mini-boom see in this fourth neutrino interpretation? The preferred parameter space by LSND is what's shown in these blue filled in regions, and these different colored contours are mini-boom's preferred parameter space. And you can see there's significant overlap between the two of these. So these are relatively consistent with one another in the context of this fourth neutrino interpretation. So where are the problems? Well, we added this new mass squared splitting, okay? And we said that there's some new mixing angle that we call sine squared 2 theta mu e that's driving this new oscillation. But this is a relatively simplified picture. In reality, this sine squared 2 theta mu e mixing angle is not physical. It comes from extending our 3x3 leptonic mixing matrix into a bigger one, a 4x4 one. And if you do that, you can identify that this effective mixing angle is actually a product of these two new mixing matrix elements, UE4 squared and U mu 4 squared. And so in order for sine squared 2 theta to be non-zero, each of these two new parameters, UE4 squared and U mu 4 squared, has to be non-zero. And if you have both of those non-zero, then not only will you have anomalous nu mu to nu e appearance at these short baselines, you'll also have anomalous electron neutrino disappearance and muon neutrino disappearance at these short baselines. And you'll see them at specifically the same baseline and energies as where you see this nu mu to nu e appearance. Additionally, you could ask, okay, what does this mean for cosmology? I said already that cosmology is one of our most precise ways of searching for evidence of neutrino masses in the universe. Cosmology is also highly sensitive to the number of relativistic degrees of freedom that are relevant at certain epochs of the universe's formation, things like cosmic microwave background formation and the formation of light elements during Big Bang nucleosynthesis. Well, if we have a new state that has a mass on the order of an electron volt that's mixing relatively strongly with the standard model via neutrino mixing, then that state will become thermalized with the rest of the standard model in the early universe and remain in thermal equilibrium, remain relativistic through these relevant cosmological epochs. And so what this figure shows is some of the regions of parameter space favored by these LSND and mini-boom anomalies, as well as some other ones that I didn't have time to mention, just showing how large the contribution to this parameter N effective would be if such a sterile neutrino existed. And such large values of N effective, 3.9 and bigger, or even 3.3 and bigger, are in severe tension with what's observed from cosmology. So if such a sterile neutrino were to exist, it could not just be a plain old sterile neutrino that interacts via mixing, because if so, it would have dramatic consequences on the cosmological evolution of the universe. Okay, so I want to return to mini boon and identify a key challenge about mini boon. I said that it's looking for electron neutrino events in its detector volume, but I skipped over this whole shaded region of different background contributions for mini boon. And what I didn't say when I showed this figure is that mini boon, while it's looking for electron type events in its detector, it cannot tell the difference between an electron or a single photon or multiple electrons or multiple photons that are all kind of collimated traveling in the same direction. For instance, one of the largest backgrounds for mini boon is this red one labeled pi naught misidentification. What this consists of is situations where a neutral current neutrino interaction happens in mini boon, creates a pi zero that decays promptly to two photons, and those two photons are either overlapping with one another, or one of them is too low energy to see, or one of them makes it outside of the detector before it starts its electromagnetic shower. All of these look like a single electron for mini boon. And so they contribute significantly to the background of mini boon's search for electron neutrinos. So one way around this is to design a detector that is better at determining what type of interactions are happening in its volume. And for this, liquid argon time projection chambers, or sometimes some of us theorists have nicknamed these colored bubble chambers, these can stand in the same place as mini boon in some cases. So this is the micro boon experiment sitting right in front of where mini boon was. And these liquid argon time projection chambers are extremely capable at telling electrons from photons, from multiple charged particle showers, etc. They give you extremely good quality for particle identification, for energy reconstruction of individual tracks of charged particles in the detector. And so microboon was designed with this question in mind, along with the SBND and Icarus experiments forming the short baseline neutrino program at Fermilab. So microboon released its first analyses relevant for electron neutrino searches back in late 2021. So these are just some highlights of those searches. And I'm not going to unpack these in too much detail, just to say that they performed this so-called template analysis where they asked, okay, if mini boon and its excess is truly driven by some sort of nu mu to nu e conversion, can we test that hypothesis in microboon? And the answer was yes, especially in these three channels down below here. They excluded the explanation from mini boon of nu mu to nu e oscillations at about 2 sigma confidence level. What they didn't do at this time that puzzled some of us phenomenologists was analyze this in the context of a sterile neutrino scenario. So some collaborators and I jumped in and we did this analysis, and we found that especially this inclusive wire cell analysis of microboon was actually really powerful at already testing much of the parameter space preferred by mini boon. So this blue curve, everything up and to the right, was excluded by microboon back in late 2021 at about 3 sigma confidence level. Let's skip over this and just move to this complete 3+1 neutrino framework. Because the plot that I showed before, hidden in that, was the fact that I was doing a simplified two-flavor analysis in the context of this effective mixing angle and this new mass squared splitting, which is what LSND and mini boon had always done previously. But if you open it up to this true 3+1 neutrino situation where we have two new mixing angles, UE4 squared and UMU 4 squared, this invokes that requirement for disappearance that I mentioned. And one of the beautiful things about microboon and its inclusive data analysis is that it includes large samples of unoscillated muon neutrinos, as well as a significant contamination of electron neutrinos in its beam. And so if this 3+1 neutrino framework is truly happening, then we should see some disappearance in our muon neutrino sample relative to our expectation, And we should see some of these green intrinsic nu-E backgrounds disappearing, as well as nu mu's oscillating into nu-E's. And so my collaborators and I put this all into one complete formalism. We found that microboom can actually do some really impressive stuff looking for muon neutrino disappearance and electron neutrino disappearance. That's relevant for the global picture of these searches for sterile neutrinos. Unfortunately, I don't have time to dive into this too much, but microboom came out with an official analysis about a year later, and we have great consistency with what they were able to test. So we were really proud of our results then. But going back to this main microboom constraint, I said that this first plot that I showed was in this simplified two-flavor analysis, where we just have an effective mixing angle that we call sine squared 2 theta against some mass squared splitting delta m squared. But I want to go one step further now and ask, okay, what happens in this panel when I let these two new parameters, UE4 squared and UMU4 squared, be truly independent with one another? It gets a little bit complicated, and what happens is I go from this plot to this one. The microboom contours have shifted slightly. My mini-boom contours have shifted slightly. My microboom contours have moved significantly to the right. They've gotten significantly weaker. Because what I've done here is that every point in this parameter space for some value of sine squared 2 theta is really this combination of 4 UE4 squared, UMU4 squared. And so in order to present these constraints, I'm actually profiling over this combination of UE4 squared, UMU4 squared onto their combination. And I'm getting weaker because I'm doing this profiling process statistically. But I want to take a closer look at this point here that's indicated by a star, where this combination of mixing angle parameters, sine squared 2 theta mu e, is equal to 4 times 10 to the minus 3. What's not obvious when you look at this plot, if you look at this star, you see, okay, this is a point that's highly consistent with mini-boon's preference for a sterile neutrino. It's inside of the mini-boon 2 sigma contour. However, it is to the left of the microboon exclusion contour at 95% confidence level. So looking at this plot, which is consistent with what the collaborations are putting out, one has the takeaway that a point like this is perfectly compatible with mini-boon and microboon. But this point is not truly a point in my parameter space. It's a family of points satisfying 4 UE4 squared, UMU4 squared equals 4 times 10 to the minus 3. That could be a case where I have large UE4 squared and small UMU4 squared, or the opposite, or somewhere in between. So let's unpack that a little bit more. What's shown here are points in this parameter space, all consistent with this blue/pink star. So the blue points correspond to large muon mixing and small electron mixing. And because mini-boon and microboon are sensitive to different combinations of those things, they yield different predictions in terms of the event rate in those detectors. So for instance, in mini-boon is pretty happy with that large muon mixing, small electron mixing combination. It has a p-value fitting to mini-boon's analysis on the level of 13%. That's something that most people would be okay with. But in contrast, if you switch the question and say that you have large electron flavored mixing and small muon flavored mixing, the prediction is this pink line, and mini-boon is much less consistent with that. It has a p-value of 0.1%. This is just one channel of mini-boon's data, so you might not be able to draw all of the relevant conclusions just looking at this figure. So A is good for mini-boon, but B is bad for mini-boon. However, if we go to microboon and do the same thing, again, microboon is sensitive to these differences as well, and microboon has the opposite takeaway. Microboon is much more compatible at a level of 5.7 units of chi-squared from its best fit point with point B, but it excludes point A at 21 units of chi-squared. And so despite this one point in this profile parameter space appearing to point to compatibility between these two experiments, mini-boon and microboon, that is simply not true. And so this profile parameter space that we, including myself, have been using for years leads to inaccurate conclusions being drawn. And so we need to move away from this type of profile parameter space. So in this paper that came out a couple months ago, my collaborators and I proposed a couple of approaches. One is to use what we call slices. So instead of profiling a three-dimensional parameter space onto a single two-dimensional parameter space, you take slices in that three-dimensional parameter space and look at two-dimensional slices for different fixed values of delta m squared. And so these are 4 different values of delta m squared for 1, ranging a few orders of magnitude. And in each one of these, what we're comparing is the preferred region of parameter space according to mini-boon in gray, with the exclusion at 95% confidence level of microboon, the solid blue lines. And what we find by and large is that there is absolutely no parameter space that mini-boon prefers at the 2 sigma confidence level that microboon is also compatible with at the 2 sigma confidence level. Going forward, we can also project to what the SBND and Icarus experiments will be able to do. And so that's what's shown by these pink dashed lines. And we see that SBN will be substantially more powerful in this regard. If you look at that kind of profile parameter space that I showed before, SBN appears to be very weak. But now when you look at slices, you recover the true power of the experiment. An alternate approach that we asked is what we call the compatibility chi-squared, where we don't really focus on any specific point in parameter space, but we ask the question, okay, where are the points in this three-dimensional parameter space that are consistent with mini-boon at some level of delta chi-squared? For instance, we could ask, where are all of the points consistent with mini-boon at 2 sigma confidence, which is about 8 units of chi-squared? And then we feed all of those points through our microboon analysis, and we ask, among those points, what is the point that is most compatible with microboon's data, and how compatible is it? And for 2 sigma in mini-boon, we get an answer of about 11 units of chi-squared in microboon. So microboon can rule out all of mini-boon's 2 sigma preferred parameter space at over 2 sigma confidence level. You can vary the consistency with mini-boon that you prefer and ask how compatible that set of points is in microboon, and you end up tracing out this blue curve. And so this star is that statement that I made before, that everything within about 2.3 sigma confidence compatibility with mini-boon is ruled out at the same confidence level by microboon. One interesting aspect of microboon's earliest data releases is that there appear to be some fluctuations that made microboon's sensitivity or made their results significantly stronger than their sensitivity expectations. Whether that's coming from statistical fluctuations or some yet undetermined systematic is an open question, but you can compare what the Asimov expectation of this procedure was from microboon, and you get this dashed blue line. So where microboon is ruling out mini-boon's 2 sigma regions at 2 sigma confidence, if everything went according to Asimov expectations, microboon would have only been able to make that statement at about a 1.5 sigma confidence level. Now, projecting forward to what SBND can offer in this regard, SBND and Icarus rather, this is where the true power of SBN shines. And so SBN will be able to blow all of mini-boon out of the water. It will be able to rule out all of mini-boon's 3 sigma preferred parameter space at almost 4 sigma. It'll be able to rule out all of mini-boon's 2 sigma parameter space at something like 5 or 6 sigma. So SBN really has power when you present the results in this context. I'm going to skip over this idea of decaying sterile neutrinos in the interest of time, but just to say that this was an approach that was proposed back in 2019 by a couple of collaborations to say that maybe this is a richer scenario where sterile neutrinos are decaying en route to the detector. And it fits well with mini-boon and LSND or cosmology in some ways of looking at things. My collaborators and I, especially my excellent PhD student Tao Zhou, tested this with microboon and found that microboon is actually extremely powerful at looking for decaying sterile neutrinos. So I'll point you in that direction if you're interested in these less vanilla sterile neutrino scenarios. But with that, I want to put this aside of new physics associated with neutrinos and think now about completely different scenarios that these same facilities can test. I'm going to take a drink of coffee while I transition. Okay, so far I've been focusing on this accelerator neutrino facility picture and how we make accelerator neutrinos in this beam. Now I want to ask the question, what else might be lurking in that beam? So at the same time that I'm making neutrinos from these charged meson decays, other new physics might be afoot. For instance, my pi zero here, if there's the existence of something like a dark photon, then my pi zero could decay into a standard model photon and a dark photon. And if that dark photon couples to some dark matter, then maybe that dark photon decays to dark matter in this A prime to chi fashion. And if that is the case, then my neutrino detector is awash, not just in a neutrino flux, but a dark matter flux. Similarly, if I have a new physics model where I consider a heavy neutral lepton, so an HNL with a mass of, let's say, a few hundred MeV, then that thing can be produced via mixing with the standard model in rare kaon decays like so. And so if a heavy neutral lepton exists, my neutrino detector can be sitting in a heavy neutral lepton flux as well as a neutrino flux. Now, how do we do anything with this? We know how neutrinos interact in the detector. What about these BSM things? Well, one example is that this dark matter flux that's passing through my neutrino detector, it could interact with electrons. It could elastically scatter off electrons in my neutrino detector. And so when you kick one of these electrons via elastic scatter, you'll see that it is a very high energy forward-going electron track in the detector. On the flip side, if we have this heavy neutral lepton flux coming through the detector, then it's possible via the same mixing that produced it, this heavy neutral lepton can decay back into standard model final states, like a standard model neutrino and a pair of charged muons. And what's interesting about both of these types of new physics signatures, this elastic electron scattering or this di-muon track signature, these both fall into these two categories that I like to think of as situations where either you might have a different spectrum from what's expected from neutrino interactions in terms of elastically scattered electrons, or you have some sort of signature like two charged muons. That's something that should never happen if we just have neutrinos passing through this detector. So we're looking for event kinematics or rare signals in these neutrino detectors driven by BSM physics. There's a whole set of detectors in neutrino facilities that are really advantageous for looking for this type of beyond the standard model physics. And depending on what type of signature you're looking for, one detector or another might be more advantageous. If you're curious about this, I'd be happy to talk more about this later. But as a simple case study, let's look at that heavy neutral lepton scenario. And let's talk about the Dune neutrino facility beam that operates in this manner. So if I run Dune for 5 years and I ask what could happen if one of these heavy neutral leptons exist, I arrive at this result. So what I'm showing is as a function of the hypothetical heavy neutral lepton mass, Mn, for a situation where this heavy neutral lepton mixes only with muon neutrino flavor, not with electron or tau neutrino flavor, I'm asking how large is the flux through my detector? How many of these ends pass through my detector if I operate for 5 years in neutrino mode? And what I find is that depending on what mass of this heavy neutral lepton I'm considering, I'll have a lot of production from one source or another. If the heavy neutral lepton is light enough, I'll see my predominant production from charged pion decay because the pion is light enough to decay into this heavy neutral lepton. If this HNL has a mass on the order of 100 MeV or so, it will be produced predominantly in charged kaon decay. And heavier masses you could produce still from things like D and D sub S decay. So I've made these heavy neutral leptons. Now what? Well, I need them to decay. And like I said, they can decay through that same mixing back into standard model final states. I mentioned this situation with a neutrino and a pair of charged muons here. This is this green line, but there's a whole slew of final states that you might experience And which state or states you decay into depends significantly on that same heavy neutral lepton mass. So for instance, if the heavy neutral lepton mass is a few hundred MeV, the preferred decay channel will be something like a charged muon and a charged pion. Now, these, what I call irrelevant decays, are in the context of the Dune detector, are final states that would be challenging for the detector to identify. So all of these are potential targets for a Dune-like analysis in this type of heavy neutral lepton scenario. So what can Dune do in this context? Well, these are three surveys of the mass of the heavy neutral lepton versus its mixing with the standard model in situations where it couples to muon flavor or electron flavor or tau flavor only. And in each of these panels, what I'm showing is the existing constraints on this parameter space in black and gray. So everything up above those black lines is already ruled out from other experiments. And then Dune's potential contributions in this context are shown in different colored regions, where each color represents one of those different final states that Dune could potentially search for. And so especially in this muon coupled case, we identified that there's a lot of parameter space in which one of these heavy neutral leptons could exist, where Dune might be able to discover it. Now, I will admit that this paper came out a long time ago. This is over 5 years ago now. There's been a lot of really good work that preceded us on this situation about heavy neutral leptons at Dune, as well as work that followed us. And what I want to highlight is the scientific enterprise is very important, that many people are working on similar topics. It's not a problem when many people want to ask similar questions, because I will argue that each of these papers found ways to improve on the things that came before it. And so as we progress towards actual data collection at Dune, it's important that we continue making such advances, making more sophisticated assumptions about what we can see in terms of the new physics or what kind of backgrounds we might expect in such a search, in order to really make sure that searches like this actually happen and happen to the level that we expect them to in these facilities. All right, so with the last 10 minutes of my talk, I want to switch gears and talk about some kind of non-standard production of BSM states that might be occurring in these facilities. So I already said before about new physics that might be produced in this kind of decay volume area from things like meson decay, pi zero decay, charged kaon decay, etc. But now I want to zoom in on this target itself. And I want to ask what's happening in there. So if I zoom in, that's my sophisticated way of zooming in. And when I think about this target, I said before it's made of something like graphite or iron. I'm going to think about that as just a collection of nuclei and electrons. Okay, so what happens when this proton beam hits the target? I said that a bunch of standard model mesons are produced. There's also a standard model electromagnetic interaction occurring. For instance, if I make a pi zero, that pi zero will decay promptly, and in the standard model, it will decay to 2 photons. And if my proton beam started at 100 GeV, those pions will have order 10 GeV of energy, and the photons that they decay into will have order 5 GeV of energy. So you have photons with order several GeV of energy passing through this target, and what will they do? They will start to shower electromagnetically. And so this is a depiction of one of those photons that's passing through, and it decides to interact with one of the nuclei in the target and pair convert into an electron-positron pair. Maybe that electron that you produced Bremsstrahlungs off another photon that itself yields another E plus E minus pair, and so on. And many, many branches of this happen as this order 5 GeV photon down converts into many, many lower energy electrons and positrons and photons. However, you see that there's many interaction vertices as this electromagnetic shower proceeds, and each of those is a potential place where new physics might be afoot. Where, instead of Bremsstrahlunging off a standard model photon, this electron might want to Bremsstrahlung off a dark photon. And so the fact that there are many, many vertices, many interactions, means that there are many, many opportunities for BSM production. Now, the big challenge with this is another schematic representation of that electromagnetic shower, is that this is our zoomed in picture of the target, but we're often interested in a detector that's relatively far away and relatively small. And so we are very sensitive to the specifics of kinematics in a simulation of what this electromagnetic shower looks like, especially as it pertains to the direction of outgoing particles. Any small effect in the direction of a BSM particle can have a profound effect on the ultimate yield that a detector might see in this context. So to attack this problem, my collaborators and I developed this code that's called PETITE. We are still hard at work on it, adding new features, adding new scenarios that I'll get to in a little bit. But I invite you to take a look at it. We're really proud of all that it can do. It simulates standard model electromagnetic showers with very good fidelity. So we did dedicated comparisons against tools like GEONT4 and the analytic results from PETITE and Wittes back in the 1960s. And it compares very well against those. And it only has a handful of standard model processes explicitly included in order to obtain these results. So this is a depiction of a standard model electromagnetic shower from PETITE, where a 10 GeV photon was injected into a slab of graphite, and out comes all of the photons, electrons, and positrons as a result. I'm going to skip over this, but this is just our laundry list of the standard model physics that is included in PETITE. And there's just a handful of processes and a couple of routines for continuous energy loss and multiple Coulomb scattering. Skip over this and get to the BSM of it all. So we made this tool with beyond the standard model physics in mind. And the challenge is that when we think about standard model physics and a photon flux that's produced from a tool like GEONT, for instance, it's mostly coming from processes like this, where an electron or a positron bremsstrahlungs off a massless photon. However, if we want to take our understanding of this standard model physics and apply it to a beyond the standard model case, for instance, where we bremsstrahlung off a dark photon with a mass of, let's say, 30 MeV, these two distributions, the kinematics and the profile of the produced vectors in this case, will be completely different. One way of thinking about this is that in the standard model case with a massless standard model photon, this process experiences soft and collinear singularities, where this photon wants to emerge in the same direction as the incoming electron with relatively low energy. And those divergences are regulated by the fact that the electron has a non-zero mass. In this case, where we're considering this BSM dark photon, this vector is much heavier, and so its mass is what regulates those singularities, and by doing so, leads to dramatically different impacts on the outgoing kinematics of this vector. And so if you take some approaches that were existing in the literature back when we started this, and you just re-weight standard model photons, you can obtain a BSM flux that's depicted in this right panel, where we're looking at the energy of the outgoing vectors versus how off-axis they are in this production scenario. Where if you treat things properly using the methods that are implemented in PETITE, you obtain a flux that's what's depicted in this center panel. And without dwelling on it, I just want to highlight how different the center panel is from this right panel. And so taking proper care in how you treat BSM production is really, really important for many experimental facilities. One such facility is Dune, and so we looked at a bunch of different BSM production mechanisms in the context of making a dark photon in Dune, and we compared our routines against some literature results, and we found that we are able to understand why our results are the way they are. We're very confident in our solid lines, and we see that they deviate from some previous literature results by up to several orders of magnitude in different parts of parameter space. So the last thing that I want to talk about is applying our knowledge about PETITE to a completely different situation. And again, this was a work that was led by my intrepid graduate student, so he deserves much of the credit here. But now, instead of thinking about neutrino facilities just for these last few minutes, I want to talk about the SHIP facility, which is a proposed detector to live at CERN. It's the Search for Hidden Particles experiment. And it will be a an experiment that's designed to look for beyond the standard model physics purely, but it operates in very much the same way of what I've motivated for neutrino facilities, where we have a source of high energy protons, in this case accelerated to 400 GeV of energy. And they hit a target, and in that target, you might produce some BSM states that travel in the forward direction. And then here's the magic of SHIP. SHIP has this 50-meter long decay chamber that they call the hidden sector decay spectrometer. And it's possible that you could have some BSM state that decays inside this volume into some set of charged standard model particles that travel in the forward direction and hit this spectrometer that is magnetized, so you can do excellent particle and reconstruction and energy measurements and identify the particles in the downstream particle ID, and really look for many beyond the standard model physics scenarios in this context. So this was recently approved at CERN. In my recollection, it is not yet funded, but it is much more on track than it seemed to be a couple of years ago. So people are getting really excited about the prospects for SHIP in the coming decade or two. Just to highlight what SHIP can do in some of these beyond the standard model cases, this is what's called a secluded dark photon scenario, where we have the mass of this new dark photon versus some kinetic mixing. These are all existing constraints from this Martin Bauer et al. Paper from 2018. And then comparisons against future projections are what's shown in the different solid lines here. And so SHIP in particular will be extremely powerful in looking for these long-lived particle scenarios. In contrast, a different scenario that's similar in spirit is one where we have a leptophilic gauge boson that couples to muon minus electron lepton number. Again, existing experiments are shown here in the filled-in regions, and then future predictions, including SHIP, are what's shown in the lines here. However, what I want to emphasize is that the previous analyses about SHIP only considered things like neutral meson decay and proton Bremsstrahlung of these dark photons. And so we looked into this for SHIP, and what we found is that we could reproduce their results in terms of standard model meson decay. So this is a flux of dark photons that you could expect to see at SHIP, depending on a certain mass and a certain kinetic mixing, depending on the number of POT. But if you added in these other production mechanisms that PETITE is designed to study, you get these other three curves. Now, for this mass, what we find is that this is not a significant, or at least not an overwhelming contribution from these new production channels. However, it does help with your sensitivity if you want to look for this type of new physics. But if we consider, instead of a dark photon, one of these leptophilic gauge boson scenarios, the picture changes dramatically. Because this leptophilic gauge boson couples directly with electrons, it is highly relevant for these different electromagnetic processes. And we see that this becomes an overwhelming flux for these types of leptophilic gauge boson scenarios. In contrast, this is what it looks like at heavier masses, for instance, 300 MeV, again, highly relevant for these leptophilic gauge boson scenarios. There are challenges associated with this. For instance, these leptophilic gauge bosons will tend to be lower energy. And so you might worry that this lower energy dark photon or leptophilic gauge boson will decay into an electron-positron pair that doesn't reach the spectrometer. We took that into account. Again, happy to talk about this offline as well. But we updated sensitivity to these scenarios. I'm going to skip over this and just get to the main result and show how we can update our SHIP sensitivity to one that includes just these meson decay constraints to one that includes all of these other channels by using something like PETITE. And so in the case of a dark photon, the main improvement is down at these low masses and relatively low couplings, where for better or worse, this parameter space is already strenuously tested by luminosity arguments about the supernova 1987A. However, it's still non-trivial. But when we switch to these leptophilic gauge boson scenarios, this is a reproduction of those meson decay production at SHIP versus external constraints. We go from this picture to this one. And so adding in these new production channels will allow SHIP to go from testing gauge boson couplings on the order of 10 to the minus 7 to a few times 10 to the minus 9. So probing much deeper in this parameter space. as well as it used to be that they could only reach masses on the order of a couple hundred MeV. That'll extend to about 400 or 500 MeV, about a factor of 2 in what these experiments can test. And then similarly for the Le minus L tau scenario, dramatic improvement in terms of what SHIP can offer. With 1 minute remaining, I just want to say one thing is that if we are lucky enough to discover some of this new physics, whether it's associated with neutrinos or not, obviously we'll celebrate. There will be champagne, there will be Nobel Prizes for everyone. But there are already people thinking, myself included, about what we could do in these facilities and in ones that might come after in order to test what that new physics is and find out new amazing features about it. And so, for instance, if we go back to that situation with the heavy neutral lepton that I talked about for Dune, you could start to ask questions about whether that heavy neutral lepton is a Dirac or Majorana fermion, which is another way of asking, do that particles interactions violate or preserve lepton number? And so if we're making these heavy neutral leptons from kaon decay, for instance, if this HNL is a Dirac fermion, then it will only want to decay into negatively charged muons and positively charged pions. But if it's a Majorana fermion, it will be just as happy to decay into a positively charged muon and a negatively charged pion. And so you could ask yourself, do these two decay chains occur with equal probability? If yes, this is a Majorana fermion. If not, it is a Dirac fermion. And because this has some mixing with the standard model neutrinos, this is deeply connected to whether the standard model neutrinos themselves are Dirac or Majorana fermions. Now, there are challenges associated with this. One is that you need a pure source of heavy neutrinos, purely coming from positively charged kaons. If you have some contamination from negatively charged kaons, this will complicate the picture. Additionally, you need a detector that can measure the charge and particle identification of these final states precisely. If you mix up a mu minus pi plus final state for a mu plus pi minus one, or if you can't tell the difference between them, you have no hope of doing this. I'm going to gloss over the details of this. Dune is one such facility where this is all true. However, the beam is not perfect and the detector is not perfect. But nevertheless, we think that there's some portions of parameter space, for instance, with muon neutrino mixing, where not only could you discover such a heavy neutral lepton, but you could also diagnose at 3 sigma confidence whether it's a Dirac or Majorana fermion. So particularly excited about these BSM situations where not only can we discover new physics, but we can say something confidently about it in the Dune era or with experiments that come in the next generation. All right, so I've talked plenty long enough. Let me just quickly summarize and offer some takeaway perspectives. I think these facilities are amazing, both in terms of what they can offer us in terms of 3-flavor neutrino oscillations, BSM neutrino oscillations, as well as these situations that have nothing to do with neutrino physics, but are BSM in their own right. Hopefully, there are new discoveries that will be lurking around the corner. If we're lucky enough that those are the case, I think that people are doing the necessary work now to prepare us for those discoveries in the next decade and beyond. But that requires a lot of work. And so PETITE is one such example of some of the work that needs to be done now that needs to introduce a lot of user friendliness as well as careful precision to make our predictions very robust for what we can look for. And so we've already applied PETITE to SHIP. There's going to be more on the horizon. Yeah, I'm happy to take any questions now. Thank you very much for your attention.
Thank you very much, Kevin, for your webinar. It is very interesting, especially all the implications for the VSM. Yeah, Walter is clapping the hands and in Zoom. So we are gonna start with the question round for all the people that are in YouTube. You can write the question. We have many in the YouTube chat, but let's start maybe with one from here from the audience in Zoom. I don't know if some of you guys has question for Kevin now. Yeah, Christoph has a question. Christoph Termes. Yes, you can ask Christoph.
Hello. Hi,
Hey, Christoph.
Kevin. How are you doing? I have actually three questions, if this is okay. So first, if you go to page 31 or to slide 31,
Yeah, sorry, one sec.
where
My
you showed,
Zoom menu I can't get out. 31, you said?
yes, okay, so or maybe 32. So
Okay.
basically what you described at the lower part, no, so there may be 30. So where you describe decay on decay to exactly this one, what is the difference between this lower scenario and the sterile decay that you had before? Because this
Good.
you would produce this always in this way, right? So this is the same.
Yeah, so this is I think, a problem in our community that we use the term sterile neutrino and heavy neutral lepton to describe fundamentally the same thing. It's a new gauge singlet fermion that mixes with the standard model. When I think about sterile neutrinos, when I use the term sterile neutrino, what I'm often thinking of is something that is light enough that it remains coherent with the rest of the neutrinos, at least as far as any experiment that you're interested in is concerned, and remains coherent, can participate in things like oscillations. And so the decaying sterile neutrino scenario I was talking about earlier is a new neutrino state that somehow has a way of decaying, probably through some additional mediator. So here, for instance, we have this new 4 that can decay via some higher dimensional operator into an electron neutrino and some massless scalar phi. This is the decaying sterile neutrino scenario. When I'm talking about a
Okay.
heavy neutral lepton, in contrast, what I have in mind is a, a new neutrino state that's so heavy that it pretty much instantly decouples from the rest of the wave packet. And then it's able to have that same mixing with the standard model that produces its decay. And its decay is happening with no new particles, no new final state particles, other than the fact that it has some new mixing with standard model. And so this
Okay,
in
but essentially it is the same, just heavier.
the same, just heavier. Yeah, yeah.
Okay. Okay, good. Thanks. Then the second question was, I don't remember the page, but you showed the result of your 3+1 analysis for the muon electron disappearance channel separately. Yeah,
This
exactly.
one? Yeah.
So I remember that more or less at the same time that you released this paper, there was a paper by Peter Denton, and I think he had like some preferred region in the electron disappearance. So what was the difference between their analysis and yours?
Yeah, so okay, I believe, if I'm not mistaken, the analysis from Peter was focused on effectively this solid blue line, which is setting the muon disappearance to 0, completely fine, and asking how much NUI disappearance there could be. And so our result in that context is this blue line at 95% confidence level. And what Peter claimed is that there is a region of preferred parameter space broadly consistent with this gallium 2 sigma island around here. And I don't remember the exact statement that he made, but I believe that he claimed that it was preferred over the null hypothesis at about 2 sigma confidence. We
Okay.
also find a best fit point in this parameter space, right around the same point as what he identified. I think the microboom collaboration has confirmed that as well. What we disagree with him on is the level of significance of that. And so we adopted the full data release from Microboom that includes their covariance matrices. And we believe that using that full covariance matrix approach that has a lot of correlated uncertainties across different energy bins. Let me, sorry, I'm losing my mouse. There we go. There's a lot of correlated uncertainty bin to bin in these types of electron neutrino analyses that makes such disappearance signals less statistically strong, less statistically preferred. So long story short, we agree with the best fit point. We just disagree with the level of significance.
Okay, so the difference is basically that you have included the covariance matrix and he didn't.
I think so.
Okay, Okay, thanks. And then the last question. So if we go back to page like 57 or 58,
Yeah.
You had like some mediator models. Exactly. So if you go from 58 to 59, why doesn't you have the supernova bound here? I think this should apply to like basically all of this B minus
Yeah.
L or L minus L alpha minus L beta models, right?
Yeah, so in principle, there should be a supernova limit down there. There is much less consensus in the literature about where such a supernova constraint should lie in these leptophilic gauge boson scenarios than in a dark photon scenario. In the dark photon scenario, this thing is coupling directly to all charged particles. And so we
Okay.
understand how supernova dynamics evolve to include that. I'm not an expert on supernova physics, but in the case where you have it coupling just to electron and muon lepton number, it gets a lot more complicated. That's kind of the long and short of it.
Okay. So
So in
no one
principle,
has
yes, there should be
done
a
it.
limit somewhere here, and we're working on that kind of physics as well and trying to make projections. What I didn't show is, so I showed electron minus muon lepton number and electron minus tau lepton number. What I did not show is L mu minus L tau, which is the third linear combination that a lot of people focus on for mu on G minus 2. A lot of reasons people like mu minus tau. We're working on that for SHIP because it's actually a lot more complicated in that context. But there are great analyses about L mu minus L tau for supernova physics from people like Sam McDermott and Juna Kroon. So there are literature results out there for L mu minus L tau.
Okay, I will have a look into that. Thank you.
Of course.
Thanks.
Okay, thank Christoph for the question. I don't know. I'm gonna start with some of the question from YouTube. I guess we have a question that is almost from the beginning of your talk, that from Aman Gupta, that he's asking, how do you choose the mass of the heavy neutral leptons? If it is a special criterion, let's say.
Yeah, so I take the approach of we should look for whatever we can with the experiments that we have. That's a little naive, of course. People like heavy neutral leptons. I skipped over this completely. From this scenario that's known as the seesaw mechanism. So I said a while ago that neutrinos have mass, but they're very small compared to the rest of the charged fermions of the standard model. One possible explanation for why that's the case is that they gain their mass through a mechanism that's completely different from the standard model Higgs mechanism. And this mechanism is called the seesaw mechanism because it consists of additional heavy neutrino states that pull down the seesaw and make the standard model neutrinos very light. And so people like heavy neutral leptons in that context, typically at a bit heavier masses, maybe hundreds of GeV, even heavier, but it can depend a lot on how they mix with the standard model. There are other reasons why you might be interested in heavy neutral leptons from the context of leptogenesis. So if these heavy neutral leptons are responsible for the baryon asymmetry of the universe via CP violation in the HNL space, leaking into the standard model. Yeah, there's a lot of reasons why you might hunt for these things. I took the approach of let's see what we can do with these experiments, and these experiments can test this 10 MeV to a few GeV range.
Cool. I guess we can wait for Aman if he can reply by the chat. But from the moment, another question that is from Shantanu Desai, that he's asking, how does one relate delta m square and sine square 2 theta to BSM theories such as MSSM, for instance, supersymmetric model, if there are some, and the second part, how it's related with the LHC searching of this kind of model, if there is a overlap.
Yeah, that's a good question. I'm not familiar with ways that you would use this to connect with the MSSM and the supersymmetric theories. if you are able to write down a mechanism in which the neutrinos obtain mass, whether it's from something like SUSY or another BSM scenario, then that will yield a set of masses for your light neutrinos, as well as a mixing among them. And if you obtain the diagonalization of that mixing of the three light states, then you can determine the mixing angles and the mass squared splittings that are present there. But it really depends on the type of mass mechanism that you're considering. So I alluded to that seesaw mechanism before. You can imagine having 3 light neutrinos and 3 heavy neutrinos. That makes a 6x6 matrix, and there are ways to study the effects on a 3x3 mixing matrix in that context. But it's pretty complicated. There are people who work on if you take that mixing and you assume that it's coming from something like a seesaw mechanism, it makes certain predictions, albeit they're very broad, about what you might be able to see in terms of LHC searches for heavy neutral leptons, that kind of thing. But again, I would say it's a very open situation where any discovery of heavy neutral leptons or similar new physics at the LHC will be very welcome from neutrino mass model builders.
Okay, thank you. I guess we can wait if Shannon too, he can reply. There are other questions, but for the sake of the time, we are gonna skip those from the YouTube. I don't know if people here, Joel or Walter, has some question for Kevin. I don't know.
I have one.
Okay.
I was wondering if you have anything to comment regarding IceCube, because IceCube has also put bounds on sterile neutrinos, right? So I don't know
Good.
if your
So,
analysis.
I skipped over this. I was talking about muon neutrino disappearance here, and I said that microboon can rule out everything to the right of these blue lines. This is an outdated IceCube line. I believe they no longer have, they've kind of changed how they interpret their results in terms of what is statistically significant. I think they have a preference for deviations from the standard model at about 95% confidence now. And it's right around in this parameter space indicated by this star. And so IceCube is pointing towards something that microboon can actually directly test. Now, it's not directly testing all of the parameter space that's preferred by IceCube, but it's right in that same part of parameter space. Minos and Minos Plus, which were older accelerator neutrino facilities, also tested that same parameter space. So I would say we don't know. It's exciting, and what's really cool about how IceCube looks for these things is it's completely different than what I laid out here in looking for this type of new physics. IceCube is actually extremely sensitive to the fact that this neutrino is a sterile neutrino. And because IceCube, these neutrinos are passing through the Earth, they're high energy. The neutrino matter interactions are actually extremely important for how IceCube looks at neutrinos. And the fact that this sterile eigenstate is not interacting leads to dramatic implications for how they look for this thing and why it's so powerful to use IceCube. So yeah, if they continue taking data and preferring deviations from the standard model, and experiments like microboon continue to rule it out, that might point us in a new direction of, not a vanilla sterile neutrino, but we need something else to explain that tension.
Okay, thank you very much.
Of course.
Okay, I guess for the sake of time, we are gonna finish here the transmission. First of all, thank you, Kevin, for your webinar. It's very interesting. It's gonna be very useful to have it in YouTube for the future people that want to refer to the topic. So for the rest of the viewers that are following us from every 2 Wednesdays, I just tell you that in 2 weeks from now, 7th of May, we have Gabriel Zapata giving a webinar. It's gonna be the webinar 179. So for all of you, for everybody, thank you very much for being here, and we are gonna see you again in the next opportunity in lawphysics. Bye.
Thank you.
Okay, the stream is stopped.
Thank you, Kevin.